Alrighty, good morning, everyone. Let's first review exam number 5, and then from there we'll move into talk about the final exam. And yeah, life will be perfect from there. E&M waves. So let's talk about this one. So first thing we really did was what? Maxwell Ampere law. So Maxwell Ampere's law here. So that's what the closed loop integral of the magnetic field dotted by the differential length is equal to, in our case, all we care about is the second part, which is mu naught times the displacement current, where our displacement current is epsilon naught times the time rate of change of the electric flux, where the electric flux is equal to the integral of the electric field dotted by the differential area. So that is Maxwell's Ampere's law. Great. After that, the next thing we did that was important was Poynting vector, which S then is equal to the electric field crossed by the magnetic field divided by mu naught. So that's that guy, where the time average of this guy, so the time average of the magnitude is what we call the intensity is equal to the RMS value of the electric field times the RMS value of the magnetic field divided by mu naught, where the RMS value of the electric field is related to the amplitude of the electric field by the square root of 2. And then same thing, of course, is true for the magnetic field. So amplitude of the magnetic field divided by the square root of 2. So that's that guy. After that, we did what? Radiation pressure. So the radiation pressure is equal to A times the intensity divided by the speed of light, where A is equal to 1 if this guy is absorbing. So the material at which the light is shining onto, or 2 if this guy is reflecting. Wood, so that's that guy. And then the last thing we did was polarization. Well, actually, let me do this. Radiation force is equal to the radiation pressure times then the cross-sectional area of the object. We do that first. And then, right, polarization is that the final intensity is equal to 1/2 of the initial intensity if it is unpolarized. But this is equal to the intensity initial times cosine squared of the angle between the two if my initial light is polarized, where theta is the angle between the new and the old polarization. So if this is my axis here, let's say this is my original polarization. So this is my original. And then my new one is, I don't know, let's say, for example, this guy here. So this is my new polarization. Let me write it this way, actually. Let me call this my original electric field. And then this is my new electric field. Then the angle theta is the theta between those two. So that's my angle. Oh, it was okay? So that's that chapter. Not too much. Life is good. Life is good. We'll talk about what to expect there in just a minute. Next up, we then did a wave optics. So wave optics is mostly what things like path length difference and then reflections and refractions and all this good stuff. So first up, path length difference. So this is Young's double slit experiments. So in this case, we had that our path length difference was equal to, in this case, this was d sine of theta, where theta depends on n, which is then equal to n times a lambda for the bright spots, i.e. constructive interference, and then n plus 1/2 times lambda for destructive interference, i.e. our dark spots. And then what was that equal to? So that was equal then to d yn over capital D, where D in this case is the distance between the two slits, and then capital D is then the distance from the slits to the screen. And then yn is the vertical distance from the central maximum to wherever it is that we're looking at, which in this case could be either dark spot or bright spot, just depends. So that is the vertical distance to that guy. Oh, I think that's right. Yes. Okay. That was okay. So that's that part. After that, we then looked at, I'm going to jump a little bit and go to thin films, because that is also the same thing. So thin films. So in this case, we have that our path length difference. So our delta D again is going to be twice the thickness of the thin film is then equal to either n times lambda or n plus 1/2 lambda. But this is lambda 2, or n plus 1/2 lambda 2 times n times lambda 2 if, in the first case, we have 0 or 2 phase changes. And then in the second case, we only have 1 phase change. Where lambda 2 is, of course, equal to the original lambda divided by the inexorable fraction of the second medium. So picture in this case is simply this. So we have n1 here, n2 here, n3 here, and then L is this thickness here of this guy. It's okay. And again, we have a phase change if we go from low to high. So phase changes occur. If we go from low inexorable fraction to high inexorable fraction. Otherwise, if we go from high to low, there is no phase change. What else did we do here? Oh, yeah. Law of reflections. Our boring thing, but law of reflections. So this is when we have a boundary B, we have the vertical, or in this case, the normal line. So our incoming ray, in this case, and our reflected ray, their angles are related to each other by the fact they're the same thing. So theta1, and then theta reflection. So law of reflections is that theta1 is equal to theta reflections. So that's our law of reflections. Finally, our law of refractions, i.e. Snell's law, says that's then related to the angle at which it goes from the one to the other. So it's a medium one has an inexorable fraction of n1, inexorable fraction of n2 is the second medium. So Snell's law, which is also known as the law of refractions. So this is our Snell's law. Simply says that what? N1 sine of theta1 must then be equal to N2 sine of theta2. Where N, of course, is related to the speed of light by the fact N is equal to the speed of light divided by the speed at which it moves within inside of the medium. Which in general, again, is a frequency-dependent object. But in our case, we're going to be dealing with monochromatic light, so we're just going to have one N value. I think that's all we did in that chapter. Okay. Finally, we have our last chapter, which is then image formations. So image formation. So here we have basically just two equations. We have our lens/mirror equation, which says that's what? 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. I'll talk about the sign conventions here in a second. And then we have magnification, which as that, what the magnification is equal to the image height divided by the object height, which is equal to negative of the image distance divided by the object distance. Let's talk about the sign rules for this guy. Sign rule number 1 is that what our focal length is positive if for lenses it is a converging lens. And then for mirrors, this is a concave mirror. And then F is a negative if we have a diverging lens or a convex mirror. So that's that guy. In this case, we have sign convention number 2. The object distance is positive if on side light is coming from. And then negative, of course, otherwise. Sign convention number 3 is that the image distance is positive if on side light is going to. Negative otherwise. And then finally, number 4, magnification is positive if it's upright. Negative if it's inverted. For combinations of these guys, only thing we need to know here is that the 2 lenses are going to be separated, or mirrors, or whatever it is, by some distance d. And then the object distance is related to the image distance by the difference between the distance between the lenses and the image distance. Last thing we did was what? The lens maker equation. I'm actually going to do that over here because I have more room over here. So lens maker equation, which says that what? If I have something that looks like this, where I have a radius 1, which deals with the left-hand side. So this is my radius 1, which in this case is defined to be positive. I have my radius 2, which deals with the right-hand side. This is my radius 2, which in this case is defined to be positive. So 1 over the focal length is equal to the index refraction of the material minus 1 times 1 over R1 plus 1 over R2. Now, of course, if it is anything different than that, it's going to be negative. So the right-hand side comes from the right-hand side. So again, if I have something that looks like this, then this is going to be a negative radius. Okay. So if the right-hand side comes from the left-hand side, that's positive. If the left-hand side comes from the right-hand side, that's also positive. So it has to come from the other side. If it doesn't, it's negative. And that's all of our equation. With okay? Too bad. So let's talk about what to expect. So first off, definitely Maxwell Ampere. So all of this stuff here will be Maxwell's Ampere's law. So in this case, think about the examples that we did in class, some sort of parallel plate capacitors, more than likely spherical. So in this case, you're going to have some sort of spherical parallel plates capacitors. So here's my parallel plate capacitors. If I look at it from the top side, it's probably going to be spherical, or not spherical, sorry, circular. And then in this case, you're going to have some sort of electric field or potential across here. So either going to know the electric field, or you're going to know the potential difference across here, where these guys are separated by some distance d. That's going to be time dependent, which means you'll have some displaced or displacement currents. And then from there, you can find some sort of magnetic field. Do a basic derivative, basically. And of course, you'll have to know anti-Lenz's law, where Lenz's law, of course, said that it is there to hinder or keep things constant, where anti-Lenz's law means it wants to blow it out, wants to drive it forward, right? Wants to make it bigger, wants to escalate everything. So definitely something like that. So that'll be a long problem, or problem number 1. Problem number 2 would, of course, deal with radiation pressures, intensities, all this kind of good stuff here. So this would be problem number 2. So in this case, you'll have to draw a free body diagram, right? Because we're going to be dealing with forces. So in this case, you'll have a light shining onto something, creating some sort of force, and then you'll probably have other forces like gravitational force, maybe tensions, other things like that. Draw your free body diagrams, and then you're dealing with all of these things simultaneously. You'll probably also have to figure out things like the intensity and then RMS velocities and things like that. One other thing I'm going to add here is remember that the ratio of the RMS velocity to the RMS magnetic field is equal to the speed of light. So that's one extra thing I'm going to add on there. So that's the relationship between the two of those. One other thing I should probably add on here, which is the slightly older thing, but remember that intensity is equal to the power divided then by, if it's a point source, that then is the surface area. But if it is a collimated beam like a laser, this is the cross-sectional area. So a cross-sectional area of this guy is collimated. But if this guy is a point source, then this will be the surface area. In this case, that's if this guy is a point source. So those are two extra things I'm going to add to that guy. So that would be the second long problem. Okay. So again, expect to draw free body diagrams and then do all that kind of good stuff. Next up, we have one problem is going to involve all this stuff here. So law of reflections with Snell's law and all that stuff. So one other thing I'm going to add on here, which I forgot to add on here, is actually remember the critical angle. So the critical angle is the angle when the light comes in and the refracted ray goes perpendicular or parallel to the boundary, which means that your final angle here, theta 2, is equal to 90 degrees. So in this case, when you look at Snell's law, you'll have n1 sine of theta 1 then is equal to simply n2. Because you'll have a sine of 90, which of course is just 1, right? So in this case, when it comes to the critical angle, so in this case, you'll have n1 sine of the critical angle is equal to simply n2. So this will be helpful for this particular problem here. This will be mostly just a whole bunch of geometry with angles and all kinds of good stuff. So some law of reflections, some law of refractions with some critical angle and stuff like that in there. So just geometry type stuff. Hopefully you guys remember geometry. Basic geometry. Be great. All right. And then finally, the last one will be, as I promised, combinations of mirrors and lenses. So it might be two lenses, it might be a lens and a mirror, might be a converging lens with a converging lens, or maybe a converging lens with a diverging lens, or a diverging lens with a concave mirror, or a diverging lens with a convex mirror, or etc. Right? But you'll have one problem, which is all combinations of lenses and mirrors. So this is number 3, and this is number 4. It was okay. One other thing I should say is inside of there will also involve the Lenz-Baker equation. Something to do with Lenz-Baker equation for that particular problem as well. It's okay. So pretty much anything else would then have to be some sort of conceptual question. So I finally remembered this morning to post the outside extra credit for this exam. So you got a couple days work on it, but it's a nice, easy one. That actually deals with polarization. That actually deals with this stuff. So this is actually your extra credit. It's a nice, simple one. Life is good. After that, yeah, so you'll probably have something with thin films, maybe something with Poynting vector, something with Young's double set experiments. I haven't decided what those are yet. That's the last thing I have to do for the exam, so don't ask me what they are because I don't know. We'll get there. I have to be there by Friday. So. That's it. Nice, easy exam. So not too bad. Not too bad. Free body diagrams. The hardest problem is usually this one, but it's pretty much exactly the same as what we've done for examples in class. So just follow the same steps. You'll be great. Yeah, otherwise, free body diagrams. That stuff is just geometry. And then the last one is all the things that we just finished, which is 2 equations. So not too bad. Nice, easy exam. Nice place, again, to make up points for. So. Any questions? What's up, Kitty? I knew you had a question. Yes.
Equation thing.
So which one?
The Young's
yes
equation. So that dyn over d. What was that again? Or like.
Oh, so that is if I wanted to determine the height or the distance away from the central maximum to either a bright spot or a dark spot. So all you're doing is you're replacing this d sine theta. So in this case, you would have dyn divided by d is equal to this stuff here.
You're replacing the leg with like the sign.
Yes, all I'm doing is replacing the sine of theta with the trigonometry. Right. So in this case, should probably draw that a little bit better. So this is then theta n.
I thought it was like another equation.
No, it's just an extension depending on what it is that I want. Yes, correct. Yeah, so this is just replacing this. So exactly. So nothing different. Any other questions? No, not too bad. Again, nice easy exam. Life would be great. Hopefully.
What if we make it so the answer we just wave our hands and finish the quantum mechanics?
I suppose you could do that as well. I mean, technically, you could do this using quantum mechanics, so that's fine. You could do that. You could do that. You could do that. Well, I mean, we're dealing with light, which has to do with quantum mechanics anyway, so it's fine. Yeah, give me some hand wavy things, say quantum mechanics, and then I'll be super excited. Any other questions? Not too bad. All right, so if there's no questions on that, let's talk about the final. Final. Alrighty, so final exam will be the same structure as last semester. So first of all, let's talk about structure. So the structure of this will be, there'll be 6 conceptual questions. And then you choose 4. Now again, if you want to do more than that, that's fine. I'll probably throw in the points from those onto there up to a certain amount of value. But anyways, these will be questions like not only just write something down, but also ranking. A lot of these will be more like ranking type questions. So inside of here would be more like ranking type questions. So you'll rank certain situations depending on what you know about the topics. So that's the first part. The second part, there are our usual problems. Those are our problems. Again, very similar to what we have on our exams now. So either 1 to 3 parts for the most part. Here, I'm going to go easy on you guys. There's only 5. 1 more than a regular exam. Nice and easy. Not too bad. So that's our structure. Make sure that, in this case, let's talk about what you can bring. So here you get 1 8.5 by 11 inch sheet of paper, which is what you're going to use for your equation sheets in this case, both front and back, piece of paper, front and back. Of course, bring a writing utensil, otherwise you got to bite your finger and use blood, or I can bring some crayons in, you can use some crayons. Other than that, calculator, brain, of course, would be the #1 thing you want to make sure you bring in. Other than that, that's pretty much it when it comes to that. So let's talk about topics. So last semester, when we had this final, the final was only based off of our major topics, which last semester, of course, was kinematics, forces, energy, and momentum. And of course, all the rotational counterparts. But basically, you had about 4 topics. If you add the rotational, that's 5 topics. Here, as we've seen throughout the semester, we have way more than 5 topics. Right. So let's talk about our major topics that we had in this class. So major topics. So first one, of course, is simple harmonic motion. So here you want to look at things like, I don't know, position versus time. So x versus t. So in this case, also energy, right? So our energy is equal to the kinetic energy plus the potential energy, which is 1/2 mv squared plus whatever the potential energy happens to be, which of course is equal to the total energy. So the total energy is equal to a constant over all times. So look at things like this. So these are kind of the main things that we looked in here. So here you have your springs, of course. So you have your springs, you have pendulums. So basically know all the differences of all the angular frequencies. So again, for Spring mass, you have square root of k over m. For a simple pendulum, you have square root of k over l. And then for the physical pendulum, you have the mgd over the moment of inertia. So things like that. So that's simple harmonic motion. Next up was waves. Waves. Let's talk about wave stuff. This was our second topic. So waves, again, you want to think about, again, our position versus, or displacement, I should say, versus position in time, path length difference, so interference type stuff. So path length difference, interference, probably intensity, things like this. So these are some things to pay attention to there. Next major topic, of course, was electricity. So our electric fields. So for electric fields, we're talking about Coulomb's law. So in this case, the force law. We're also talking about Coulomb's law when it comes to the electric field. So calculating electric fields. And then the other major one would be Gauss's law. So I would probably 1000% expect to find some sort of Gauss's law problem on there. Probably a graph, yeah. A picture, do cool things like that. Number 4 would then be potentials. So things about potentials, like how it relates to an electric field. So delta V is equal to minus that integral there. Also, the electric field is equal to minus the gradient of the potential. Things like that. Maybe potentials of point charges. So my potential of a point charge, KQ over R. So things like that. The potential at a given point, K integral of dq over R. So those kind of things to pay attention to. So those are my potentials. Next up, number 5, we have our circuit stuff. So for circuits, we have what? Capacitors, resistors, Kirchhoff's laws. So again, I would be 1000% ready for Kirchhoff loop rule problem. Right, very similar to what we have on the exam. So that's our major topics there. Next up, we had what? Magnetism, right? So finally, number 6. Let's do that in red. Magnetism. So magnetism, that's a really weird looking magnetism. There we go, magnetism. So here we had what? Force on a charged particle. So force on a Q, we had force on a wire. What else did we have? We had Ampere's law without the Maxwell connection to that. We have Biot-Savart's law, but we never really did anything with Biot-Savart's law, so I wouldn't worry too much about that. And then we have Faraday's law. Faraday's law is another one I would pretty much 100% expect on there. Now, on the exam that we did motional EMF. So I would expect to not do motional EMF and do some other variation of Faraday's law, which again says that the EMF, which is equal to the closed loop integral of the electric field dotted by the differential length, is then equal to minus the time rate of change of the integral of the magnetic field dotted by the differential area. So maybe expect some sort of time-changing magnetic field or something like that, but not a motional EMF. So no motional EMF in this case. So no motional EMF. So that type of thing. So again, kind of the major topics inside of major topics, expect to see all those kind of things. So again, Gauss's law, integrals for like electric fields, possibly Coulomb's law. So again, a lot of the things that I mentioned here are major topics inside of major topics. So putting all the questions we have together, that is what, 11 questions. Each one of the questions will deal with only solely one of these things. But basically, all of these things will be represented on there through a problem or a conceptual question. Okay. What's up, Kitty?
So in addition to the 5.
Right. So we have the 5, and then we have the 6.
Oh, you're saying that these are the major topics.
These are all the major topics, which will every single problem, including the conceptual questions, will deal with one of these major topics. Oh, no, you're fine. And again, when I say major topics, I mean one of these subtopics within inside of a topic.
I thought you were saying in addition to the 5 problems, we are also going to have one of each of these.
No. Gotcha. No, so for example, in magnetism, I would definitely expect to see Ampere's law and definitely expect to see Faraday's law because they're two of Maxwell's equations, right? Just like over here, I would definitely expect to see Gauss's law, either something to do with integrals for electric fields or maybe Coulomb forces and things like that. So again, these are major things with inside of major things. If that kind of makes sense. Mia, you had a question. What do you have? I saw somebody's hand in this ballpark. That was you? Okay. Sorry, Jamie.
What problems like are those gonna be the ones you like underline, or are those concept? Or could it be either or?
Either or. Now, the ones I would say definitely calculation wise would be for the main problems would be Kirchhoff, probably Faraday, Gauss. These would be 3 of the 5, I would say. Otherwise, yeah, all the other topics would be based off of probably conceptual. Yeah, now it's your turn.
That's on Friday.
Yep.
Or how would that?
No, so anything that we take on this exam on Friday will not be part of the final.
Oh, we did last year.
Yeah, just like we did last year. Okay, fair enough. Yeah, so the exam will only cover, the final will only cover exams 1 through 4, not exam number 5. So I was not clear on that. Gideon, what's up?
Isn't that delta B under the potential? Like the negative delta B equals negative.
Oh, no, so that's a line. So this one's a line, and that's a negative. Is that better?
Yeah.
So delta V is minus integral. I just didn't want to write the whole thing out, but minus.
Okay.
There you go. No double negatives in this case. No. What's that?
And we get the sheet of paper.
Full sheet of paper, 8.5 by 11, all that good stuff that you want to write on it. I mean, if you want, if you don't trust your own handwriting, then yes, that's fine. Gabby, what's up?
Are you able to give us like a general idea of what the other 2 big problems are? If not, that's fine, but
I'll have to remember. It's been a while. So give me a minute. We're not gonna lie, Gabby. All right, let's see here. All right. Come here. I do have to make some modifications to this, but where is it? There it is. All right. So in the form that I have here, one would be Kirchhoff's loop rules, as I said. One is Faraday's law. One is actually Coulomb's law with forces of between charged particles, superposition. So force between charged particles, and Gauss's law. Looks like I do have an extra credit on here, so that's amazing. So that is finding the potential from a continuous charge distribution. That's what I'm looking for. And then finally, the last one was a circuit with capacitors. So parallel series type stuff. What's up, kid? That was a test that I've used for several years. Yes. I haven't changed it much.
Wait till there's extra credit.
There is an extra credit on there. Yes.
Okay, I do have a question.
Yes.
The extra 2 conceptual questions, that also extra credit on it.
Probably. I haven't quite decided yet, but yes, maybe from one of them, but we'll see.
We just have to do. I guess we have, if we do.
I would say do all, and then I'll take your best from them, and then decide what I'm going to do with the other part. What's that? There you go. There you go. Cool. Yeah, so it looks like all of the other ones are pretty much ranking questions, things like that for the short answer. I do have 2 calculation ones on here, so I'll have to change those, but that's cool. So,
Are these answers with other examples posted up?
I think some of them yes, some of them no, so I'll make sure they all show up on there in the next day or so on here. What's up, Mia?
Example, like questions that we did.
Oh, you mean like the in-class examples?
Yeah, I have all the work right now, but I don't have the questions.
Oh, so you just want me to post the questions?
Yeah.
Yeah, I can do that. I can do that. Send me an email or remind me. Okay. You are. I don't know. Think I got all kinds of time in the world, but no, that's fine. What's up?
Can I just bring in the four equations?
Yeah, if you want to bring in the 4 equation sheets, if you still have them, that's absolutely fine. Yeah. Yeah. So you can either bring in 4 index cards or the sheet of paper. Yeah. Or you can tape them to that or whatever you want. Yeah. Whatever. Any of those are fine.
But like, as you said, to double check that.
Bring in both.
Just in case we forget to bring.
We'll see. We'll see. We'll see. I'm not going to give you a definite answer at the moment, but I'll ponder. I'll ponder. What's up, Gavin? Yep. Potential.
Okay.
So calculate the potential of some continuous charge distribution. Yeah. What's up, Gavin?
Like which part, specific part
Oh, that's
from the. Yeah.
talk about the problem I mentioned. So that's this. So Coulomb's law between charged particles. Yeah. Yeah. That was okay? Now that you asked basically everything that's on the exam at this stage.
Wait.
That is true. You know I'm too nice about these things, but yeah. Oh God, I have no idea. Usually pretty good.
What would you guess?
Well, I can look at previous years if that's what you want to know.
Okay.
Let's see here. Grades, there we go. So let's look at last year. Let's see how they did for last year.
Yes.
Mhm. All right, so that is what column? So this one. So the average last year was about a 150 out of 200 points. So that's what, a 75. So
So that's
better than most of them. Yeah.
except for that's better than everything but the first.
Possibly. I don't quite remember. My brain works sometimes, but not all the time. So.
Because it was 77. But I think another one was 77. Like
Something like that. I know we had a few good ones in here. So
an example.
yeah. So typically I would say it's somewhere between like 70 and 80 for the final. Is typically the average for that.
What percentage?
Oh, so the final is worth 200 out of the 750 points. I think we have 750, right? 750. Anything else you want to know about or from maybe since I'm being overly happy about you? Okay. Well, I've already told you enough of that, but I won't go that far, but you know. I do have limits somewhere. What's up, Bowie? Is that a hand or just talking? Did I see Wicked 2? I never saw Wicked 1. So not my typical cup of tea, but that's okay. Is that another one?
So they think we do some sort of like answer from one of the older ones, like just a simple one. If we have time.
From one of the older ones.
From one of the older chapters, like maybe like.
Oh.
This one, something like that.
I mean, I suppose we could, if you had something in mind.
No, like. Like.
All right. I'll think about it. So just to remind you, tomorrow we will not have class, at least officially. I will be here. So if you plan on coming in, I will be here to answer questions and things like that. We can probably work on a problem then. That'd probably be a little better. We'd have more time because we got less than 10 minutes now. So what's up? You mean like right now?
Yeah.
Okay.
Is there any way?
Yeah, that's fine.
Okay.
You got a particular one you want to talk about?
Yeah. It's the one with, it's the polar.
Yeah.
Oh.
And I don't really.
We can do that. Polarization one for this one. Okay. So I guess we're going to work on the polarization problem from the group assignments. So if you want to hang out for that, fantastic. If not, that's fantastic as well. I got to find it first. There it is. All right. So let's talk about this guy real quick. Where's my eraser? There it is. All right, so this thing says, we have unpolarized light, which has an initial intensity of 43 watts per meter squared. And then we're going to run that through two polarizers, where in this case, we have this guy, which is at a 70 degree. So, right, so this is at 70 degrees here. So this is my polarization axis here. So this is 70 degrees. And then the next one is going to be at 90 degrees. So this one is polarized this way, and it wants to know what is the final intensity. So let's talk about this. So my initial intensity comes in, it comes through this one. So I'm going to have an I1. Since it's unpolarized, that means I1 is going to be I0 divided by 2. So that's going to be that guy. And then finally, it's going to come through here, which means that I2 by Amalis's law will be I1 times cosine squared of the angle of theta, which in this case is, if I superimpose this guy on here, so I know this is 70, this is 90, so it's going to be, the angle between the two of those, so it's going to be this angle. So that's going to be simply 20 degrees. So putting everything together, this is going to be 1/2 I0 times cosine squared of 20 degrees, right? So it's going to be 43 divided by 2 times cosine squared of 20. That's it. Rest is now plug and chug. So according to this, you should get 19 watts per meter squared. If that's correct. Which I think it is. Yep.
For like unpolarized.
Yeah, so anytime I have unpolarized going through any polarizer, doesn't matter what it is, it automatically will drop by a factor of 2.
But once it's already polarized, angle.
Correct. So you use the angle between the previous and the new one. Yeah. Yeah. So that angle is always the angle between the two polarization axes.
Okay.
Yeah. So the old one and the new one. So.
It had been so long since we did this in class because of like Thanksgiving.
Right.
And everything that I didn't want to bug you as much tomorrow about it.
Fair enough. Fair enough.
We can do it today. Yeah.
Exactly. Exactly. All right. So any final questions? Everybody's okay? All right. So maybe I'll see you tomorrow. Otherwise, I'll see people on Friday, and then I'll see people on the other Friday. And then if you need me before that, you know where to find me. What's up? And then, well, I mean, people come and see me after that.
We'll be working for that experience.